And off we go. Okay, so here's where we left off last time. We finished section 1.1, and I believe, if I remember correctly, I did not start with section 1.2, so I'm picking up here. We're going to talk about something called a parameterization. It is a way to represent a curve with a function. Now, y'all have already seen some ways to represent curves with functions. So, for example, sometimes a curve is a graph of a function. Sometimes a curve is represented with an equation. An equation could be argued to, relate in some way to certain kinds of functions. So, different ways that y'all have seen in the past to use algebra to represent geometry. Okay, so this is just a new one of those. And in particular, here's how a parameterization works. A parameterization gives position as a function of, I'm going to say, time. It just rolls off the tongue a little bit more nicely, a little bit more succinct. Position as a function of time. Now, technically, it could be any scalar parameter. You could imagine that scalar parameter as any, you could imagine it as some sort of an angle, or you could imagine it as whatever, who cares? But very often, and certainly as you're trying to build intuition for parameterizations, I think it's helpful to think of it as time. So position as a function of time. Now, I have a gesture that I think is helpful to understanding, what does this mean? And that is, follow the tip of my finger, just kind of do like this. And notice, at any given moment in time, at a particular time, I have a position. So literally, this gesture of moving your finger around like that is giving position as a function of time. That is a parameterization. A parameterization effectively is the act of drawing a curve. Does that make sense to everybody? When you draw a curve, your pencil is at a particular position that depends on time as you do the drawing. Okay, all right, so let's see some examples. Here is a parameterization. Notice position's a function of time because position given by x and y coordinates, which you might abbreviate by, let's say, we'll call it the x vector. And those coordinates are functions of time. So literally, position is a function of time. And now to be more explicit, the explicit functions are that x coordinate is given by cosine t, and the y coordinate is given by sine t. And that's just a arbitrary parameterization. And I kind of pulled out of thin air. Now, we've made the observation that parameterizations draw a curve. What curve is this drawing? Yeah, so somebody got it already. There's an idea here, and that is to recall that these formulas, we know a relationship. A lucky break. And you don't always get this lucky, but we happen to have a lucky break here. We know a relationship between those functions. In particular, they satisfy this relationship. In particular, x being cosine t and y being sine t, I know that parameterization satisfies this relationship because cosine squared plus sine squared is indeed 1. So what that means is every point that is traced out by this parameterization satisfies this equation. Or said differently, every point that is created by this parameterization is on the unit circle. So that is a parameterization of the unit circle. It just kind of draws the unit circle, kind of like this. Everybody on board with that? All right. Bad news. You won't always get lucky like this. We got really lucky with this exercise where it happened to be that not only was there a convenient pre-existing relationship that we knew between x and y, but we even noticed their relationship as well. So what if you don't get so lucky? And there are various different techniques that you can use. I'm going to show you a few of them. For whatever it's worth, it's just an unavoidable reality that when you're trying to figure out what is this parameterization I've been given, there is no single method that you can just decide I'm always going to do it this way. You need various different approaches for various different circumstances. So my favorite metaphor along these lines is to think of every one of these methods as being a tool, and when you have various tools that you use for various circumstances, I like to think of that as tools in a toolbox. So I say that a lot. I think it's a perfect metaphor for the circumstance, and so we're going to go through various tools that you should put in your intellectual toolbox. Okay, so what's this? All right. Well, different ways I can approach this. First question: Do I remember any pre-existing relationship that I happened to have memorized in a class years ago between these functions? No, of course not. Absolutely not. I've never seen these things before. So no such luck as in the previous example. But here's what I can do. Don't forget, when you describe position, the first coordinate of what you're describing is probably what you're going to call x. And likewise, the second coordinate is presumably what you're going to call y. So this doesn't just say t minus 1. This says x equals t minus 1. And if you then solve for t, you get that? And having solved for that t, if you plug that in there, this formula for y, let's see here, this formula for y turns into this. So solve for t in one of the equations, plug it into the other equation. And the result, y'all can, again, the details, y'all are good at algebra. Make sure you follow all the details. That's a good sort of after-class thing to go through and check the algebra. Notice the result is, in fact, kind of familiar, right? This is an equation of a line, flashbacks to high school algebra, and so we know what that is now. I saw a hand a second ago, and yes?
So what would we use this for?
Oh, if you encounter this parameterization at some point or some other parameterization and you want to know what it is. So sometimes sometimes you encounter things and you want to know what that looks like. And so this allows us to conclude, that's this very familiar line that we've seen back in high school algebra. Is that cool?
Okay, so that just shows that vector exists in that.
What that shows, so this is a parameterization, right? This is a function that traces out some curve. Okay. And now as a result of this argument, I know that the curve that it's tracing out is a line. Okay. Yeah. Okay. Everybody happy? All right, now, here is a different approach that works in different circumstances. Keeping in mind that this, again, is x, and this, again, is y. Let me just explicitly write down that's what x is. And now, if we look at these formulas for x and y, so let's see, again, there's my x and there's my y. You look at the x and the y, and I'm just going to kind of notice that they look a lot like each other. Lucky break. They won't always, right? But sometimes they kind of look alike. And when they do, when you can kind of see how they're very similar, they're connected in some seemingly not so weird way, think about how you would turn one of them into the other one. And in this case, notice I can take this formula t minus 1, and all I've got to do is multiply by 3 and add 7. And the result is the formula that I have for y. So this process of turning the formula for x into the formula for y, I was motivated into by seeing this sort of relationship, sort of the similarity of these expressions. Now, of course, you got to be legal. If I do it to the left side, I got to do it to the right side. And having done that, check it out. I again get this same resulting equation. So that's a different way to get to the same result, capitalizing on a different aspect of this particular example. How are we doing? All right, so why am I showing you all these multiple methods? Well, because some of them won't work in a lot of circumstances. And again, the more tools you have in your toolbox, the more likely it is you're going to be able to solve your problem. If you want to get a screw and put it into a board, you don't use a hammer, right? You need the right tool for the right job. So let's suppose that this example had been different. Let's suppose that this right here wasn't easy to solve for t. What if that were a cubic polynomial in t? Then I can't solve for t. And if I can't solve for t, then this whole method is useless. You know what I mean? Okay. On the other hand, let's suppose that these two expressions. What if there was just no particularly obvious relationship between them? What if they didn't really look that much alike? What if one of them had cosecant in it and the other one had an exponential in it? Then I've got nothing. I can't. Then this whole method, right, would be useless. So different tools for different scenarios, and always tailor. Always select the tool based on what you've got to work with in the situation at hand. Okay. 3-dimensional example. So this is 3-dimensional because my position has 3 coordinates. That means I'm in 3 dimensions. So this is tracing out a curve in 3 dimensions. I am not optimistic on finding an equation. Equations, we're going to see a lot of this later, but equations in 3 dimensions tend to make surfaces. There's a few counterexamples, but generically, equations make surfaces. So we've got a curve. Well, I know it's a curve because, again, it's a parameterized curve. We are drawing out position as a function of time, and that just makes curves. It does, right? Okay, so a different tool for your toolbox. In this case, lucky break, I'm going to capitalize on what I've got. I recognize that part. We've seen it before. That was our first example. I know what that is. That's a circle. Now, that's only the x and y coordinates. That's not my curve, right? But since it's only my x and y coordinates, in fact, I understand how to get x and y coordinates, and that is from projection. If you have points in 3-dimensional space, projection to the xy plane, right? This vertical smushing is going to take a point with 3 coordinates, and it's going to return just x and y, namely 2 coordinates. And so I know, just from looking at this part right here, I don't know the curve itself, but I do know that its projection is a circle. So what you might call its shadow in the xy plane is a circle. Everybody on board? That's a nice observation. It's useful sometimes. Next observation related. Let's look at that third coordinate, just t. Well, of course, that's telling me just the z coordinate. I'm going to note you can view that as projection to the z-axis. So take all of space and imagine sort of squeezing it down, sort of squishing it inward toward the z-axis like that, right? And that, I can't say I know what it is. I guess it's just the z-axis, right? Because t starts at 0 and then just kind of goes up. So altogether, we know 2 things about this curve. Again, still don't know the curve. But I do know that its shadow is doing this, and I know that its altitude is doing that. And now you just have to use your geometric intuition, and altogether, what curve is it? Oh, 2 seconds. What curve is it whose shadow is going around in circles and whose altitude is rising at a constant rate, and it's this thing like that, which is called a helix. Yeah, question?
How do you know it's going to be
Well, because it says so right here, z is t. And so as t increases, what does z do? Well, z is t, so it increases. Is that satisfying?
Yeah.
Okay, yeah.
Yeah. I think what else is doing is a function of time, and time
Yep.
is going...
Yeah, absolutely. Yes?
Yeah, and along the same line, like how would you know it with the X and Y?
How do you know which way it's going?
Yeah.
That's a great question. I did kind of gloss over that. Let's go back to this first example here. So I'm going to say point plotting. Right. So in other words, if you just take t equals 0 and plug it in and see where you are, then you're at a certain point, and then just kind of look and see what happens as t slowly rises, and you'll notice that it's going counterclockwise. Nah, it's just kind of direct observation. Yeah, we are going to talk about another method that will address that better, but it's going to use derivatives of parametric curves, and that's going to come in a couple of weeks. It'll be a bit. Yeah.
Okay, so if you want to, like with the plots, you're going to substitute t for both X and Y.
Well, you're going to substitute t for t in both of these formulas. That's right, in both of these formulas. That's right. Yep. So x and y are functions of the same t. Absolutely. Yeah. Okay. Yes.
So if it were moving in a different direction, it would be like a negative sign, maybe? Or negative?
If it sounds like you're proposing a different question, is that right?
Like, a different question if the helix were moving clockwise.
Yeah. So there's different ways to the problem with. So I would need to know exactly what your different question is, and then we can talk about how to deal with that. It is true that if I were to stick a minus sign in here, that it would make it go clockwise, and if I were to stick a minus sign instead here, that would also make it go clockwise. But there's a lot of geometry going on there that's kind of I'm going to say it's a distraction from the point of this. Yeah, but is that satisfying?
Yes, that's
Okay. Cool. All right. Next question. What if we want to go the other way? Every example we've seen so far, I gave you a parameterization. The question is, what's the curve? Now we're going to entertain, suppose I give you a curve. How would you find a parameterization? Right? And this act, by the way, of finding a parameterization is called parametrizing the curve. How do we parameterize curves? There are, again, tools for your toolbox. There's no single method. There's kind of a bunch of them. I'm going to start with my favorite. This is my desert island curve parameterization technique, and it's called the graph parameterization. The big condition on this method is that your curve must be a graph. You must be able to solve for one of the variables as a function of only the other variable. Now, I emphasize, not every curve has this feature. Not every curve is a graph. Y'all probably remember the vertical line test from way back when, right? So, it only works for graphs. But if you do have a graph, here's how easy it is. If you have a graph, whatever is the input variable, let t equal to that input variable, and it just kind of falls in your lap. It's that easy. It's very algorithmic. It's very plug in and celebrate. There's not that much to it. Let's see an example. Looking at this example right here, let's look at this curve, and note it is indeed a graph. Right? Y, one of the variables, is solved for as a function of the other variable, which means that x is my input variable. As instructed, I'm going to let x then equal to t, and I claim we've already won. It's already over. Just following this instruction, let t be the input variable. Because here's the thing, if I let x equal to t, then, that means I kind of have to let y be t squared. And done. Right now I have position as a function of time, victory. Yes?
If you let y equal to t, you get like root t and
Yeah, it doesn't work. Yeah, crash and burn, that's not the method.
It doesn't work.
Yeah. So and I don't want to get into basically. The scenario is, I want to show you good methods that will work, right? And if you stay on the path that I describe, then you won't get into the brambles. And I don't really want to talk about how to get unstuck from brambles. Yeah. So there's a lot of ugly things that can happen. That's right. Does that make sense? Yeah. Okay. How we doing? Yes.
So the first thing, if we're given a graph and a function, we want us to put x t.
Do what now?
Like set x equals t.
You identify what is the input variable, right? So step one, identify that it is a graph. Step two, identify what is the input variable, and whatever that input variable is, let that equal to t. So let me give you another example, and let me clean up the mess that I've made here. Another example here. Let's look at this equation. Not currently written as a graph. I have not solved for one of the variables as a function of the others. And initially you might be discouraged when you see something like this because you might try to solve for y, and you can't solve for y because it's all transcendental and stuff, right? It's not going to work. Okay, but remember, there's no particular law that says which variable you have to solve for. And in fact, it's quite easy to solve for x. And so even though it wasn't given as a graph, I can rewrite it as a graph. And now x, which is one of the variables, is a function of the other variable. In this case, y is my input variable, so I'm going to let y be equal to t. And again, it's all over but the shouting, because after all, if y is equal to t, then you plug that into there, and that means that x must equal to this business here. And success, we have position as a function of time. And we have a parameterization. Everybody good? Okay, so graph parameterization, you kind of love it. It's so easy and it applies in a very large number of circumstances. It's definitely first thing to look at in most cases. Now here we have a question. Yeah.
What if there's more than one variable?
Then you have there are endless parameterizations of any curve. Yeah, so the parameterizations are not unique. And if the question asks you to find a parameterization, any parameterization will do.
No, but I mean, like, if there's x, y, and z, then how do you...
Oh, right, then that's not a graph.
Okay.
Yeah, that's right. It wouldn't be a graph, and that method only works for graphs. That's right. Yep.
Quick question. The reason why we did y equals c is because y is the input variable in this case?
Yep. That's right.
So it depends on what you need the subject to do.
Yeah, you have to interpret your given equation as a graph. You have to have one variable as a function of the other, and whichever one is that other, that's your t. Yep. Cool. All right. So now here's another method. Again, the graph parameterization will not always work. Sometimes your curve is not a graph. Sometimes, even if it is a graph, sometimes it just doesn't work out algebraically. And this is a nice example of that. So what we have in this example is a wheel. Imagine this being a wheel right here. And this big dot at the bottom of this wheel is a reflector. Imagine this being like a bicycle wheel, and this is you know how bicycle wheels have the reflector down on the, okay. And now imagine that is rolling along the x-axis, like so. And now follow my thumb here, right? As it rolls, the reflector is going to trace out a curve about like that. And so let's see here, I'll use orange here. There's our reflector. And as the wheel rolls, it makes a curve that starts off anyway about like that. And I'm sure y'all have all seen bicycles rolling down the street at night or dusk or whatever, and the street lights are on, the reflector catches, and you get this kind of herky-jerky kind of path, right? So we're going to parameterize that path. Now, if you were to try to write an equation for that curve, you're going to fail. It's very hard. It does not work out well as an equation or as a graph of a function. It is a graph of a function, but finding that function is intractable. You just kind of can't do it. So, yeah, question.
Could you please repeat how you got to that path?
Oh, this is just geometric intuition. But if you try to think through as this wheel rolls, right, and think about how this point moves, and as it rolls, it kind of rotates around, but the wheel's also moving, and I claim it makes some path. Yeah. Right. Yes.
So if you're asked to parameterize, like generally speaking, you first look at like what's method 1, can I do that, and what's method 2.
You've got a box full of tools, and you're going to fish around through your toolbox until you find the tool that works best. The best way to get really good at identifying the right tools is to spend a bunch of time in your workshop. I'm extending the metaphor. Trying to build things and working with your tools, and you'll develop a good intuition for which ones are going to be useful in which circumstances. I wish that there were some cues, like, whenever you see this, use that tool. And it's just not really, that's just not quite how it works. So, sorry for the bad news on that. Right? Yeah. Okay, so let's talk about this method here. There's a few aspects of this question that I think are the most critical. There are also a bunch of details that are involved, and as I've noted, tough choices and course packed full of material, et cetera, I have to be very careful about how I spend class time. The details of this example are going to be for y'all to read through on your own. And this is a healthy exercise. You want to make sure that you can do that. I am going to hit the highlights. I'm going to show the big points, what really matters in this. And the trig of it all, and the algebra and the details of it all, y'all can fill in the blanks. And again, healthy exercise to make sure you can do that. Okay, so the first big idea. When you have your diagram, and remember, here's our reflector, right? We're going to try to understand this path by looking at this particular moment and writing a formula for that position of the reflector. Make sure that you have unambiguously and clearly chosen and labeled your parameter. So T. Make sure that it is clear to you and clear to your reader. What is T? Now, I've made a choice here. There's always a million choices as to how you could have set this up, and I am going to notice that we have a straight down direction that we can talk about, and then there's also this the worst line ever. There is the direction of the spoke that has the reflector on it. And I'm going to define T to be this angle, like so. That's T. Now, why did I make that choice? There's a couple nice things about this choice. For one thing, when T equals 0, we're at the beginning. And I kind of like it. This is not necessary, not required, but I find it, satisfying when at the start T equals 0. Another thing that's nice, not technically required, but intuitively nice, is if as time passes, if T, your parameter, is actually increasing. Right? It would be a little bit weird to have a parameterization based on a parameter that's moving backwards in time. That's just, it's not that you can't do it, but it's, oh my gosh, it's so confusing. And you don't want to do that if you can possibly avoid it. So notice that this T has that feature. As the wheel rolls, that T gets bigger. Right? Last thing I'll note that when you have angles and circles and stuff like that involved in your question, very often it's a good idea to let your parameter be one of those angles. Because trig works better one direction than the other. I'd rather deal with sine and cosine than arc sine and arc cosine. So you let T be an angle, and you're probably going to be dealing with the preferred of those two options. All right, so that's the first big point. Be very clear and careful about how you define your parameter. Okay, next big point. Very often, this is a great example of it. Very often, the point that you are interested in, let's see here, let me clean up my mess. Very often, the point that you are interested in is a sum of simpler things. Now, there's our point. There's our reflector. I claim that that's the sum of the position of the axle and what I'm going to call this displacement D vector, basically defining that spoke of the wheel. So blue plus green equals orange. Yeah? And I claim this is really, really helpful breakdown. Let me explain why. That axle is doing something very simple. The axle is just moving in a straight line, and that's going to be relatively easy, isn't it? So that's going to be an easy thing to deal with. Now let's talk about the green arrow there. That's inadvertent reference to a comment. The green arrow here, a lot of people think of it as kind of doing something like this, and that it's both rotating and moving. I don't really need to worry about the moving part of that. It's a vector. Vectors don't really have position, right? I mean, the arrow that I use to represent a vector, I guess technically has a position, but vectors don't have a position. I don't need to know where this green arrow is. I only need to know which direction does it point and what is its magnitude. That's all I really need. Right? And so that green arrow is actually also pretty easy to understand. Let me come down here to where I have that drawn. That green arrow, here we go, about like that. Well, as the wheel rolls, it's just kind of going around in a circle. Circles are pretty easy to deal with. Does that make sense? So I'm going to say we've got a foot in the door here. And this is a really nice first, second, I guess, step. We've broken down this wacky, weird orange path that I don't even know how I'm going to get my foot in the door on being able to describe it. I've broken it down into a line plus a circle in some sense. So massive victory. Everybody good? All right, here's the last big point. It has to do with the axle. Reminder, our axle is at this location right here. And okay, so here's the big point. Keep in mind, we started off over here. The wheel was touching right there at the origin. As it's rotated, there's a certain amount of road that has touched the rubber of the wheel. This is all these points that I have highlighted down here on the X. These are the points that have touched rubber. Okay. Notice that distance is the X coordinate of my axle. How about that? Okay, whatever. The really cool observation, now this is just a physics kind of, not even physics, just a geometric, intuitive physical appeal. The amount of road that has touched rubber has to equal to the amount of rubber that has touched road. This is basically just a way of observing that the wheel is not slipping or skidding or anything like that. The amount of road is equal to the amount of rubber. You got to kind of roll that around in your head a little bit, but I hope that makes sense. Everybody kind of see how that works? Okay. So why is this helpful? Well, keep in mind, I've defined my parameter to be this angle. So I can use T to help me understand this green arc length, namely the amount of rubber. And then I can just immediately say, oh, well, the amount of that rubber, that's the amount of road, that's then the X coordinate. of this axle. So that's the last of the three sort of clever essential ideas for making this question work. So with those three essential ideas established, the rest is details. There is a little bit of trig involved. I hope y'all remember your trig. It's in the prerequisite trail for this course. I'm going to assume that y'all are good with trig, right? By the way, I forgot to mention this in the other classes. I'll need to say it tomorrow or Friday. I am going to assume that y'all remember your angle addition formulas for sine and cosine. Just sine and cosine. Forget about tangent and stuff, right? But sine and cosine, angle addition formulas, you need to know. And that's how I get from here to here, is by plugging in this into there and using the angle addition formula. So make sure you're good with angle addition formulas for sine and cosine. And everything else in the rest of this example is just details. So this will be a fine exercise for you all to think through, make sure you can fit the pieces together, and all together, there's your answer. Okay, if you get stuck, come ask me questions in office hours. Happy to help. Yeah.
Yeah, I just wanted more, like, if you could explain a bit again about the load and the rudder.
Yeah, so this is kind of a physical appeal. Let's see how to say this. Well, imagine that we were looking at just a teeny tiny amount of rotation. So here the wheel has rotated quite a distance, right? So let me draw a different picture here where it has rotated much less distant. You know what? I'm just going to do it right on here. So much less distance. And so I'm going to draw. I'm going to cheat by tracing, and then I'm gonna do like I made it harder on myself. Okay, I think that worked. Okay. So now it's rolled just a little bit, right? Now where is the reflector at this point? Well, the reflector would be about there because it's kind of just getting started and going like that. And now let's look at this picture, and where is the road that has touched rubber is about like this. And the rubber that has touched road is about like that. And you can see they're basically the same little curve. You see what I'm saying? And so as it rolls, it keeps being, each little bit is just all the same. Is it? Good. All right. Yes?
I understand that part, but how do you use that then?
Yeah. So the idea is that we need to know that distance because it's the x-coordinate. And it's nice to know that that's equal to that distance because we know that, colors. We know that angle, right? In high school geometry, it lets us use this angle to compute that arc length, and this arc length is the same as that distance, which is the x-coordinate.
So you're setting that equal, how do you know, like, how long the blue is?
The blue is equal to the green. That's the big point, is that blue equals green.
But how do you know what the green is?
High school geometry. This sounds like an office hours thing. Let's talk after. Yeah. Okay. So there's an old high school geometry formula about arc lengths of circles. Yeah. Okay. Where am I? Oh, okay. Yeah. Quickly.
Yeah. Would we need to also calculate the y coordinate? Because you wanted to.
A little louder. I'm sorry.
Would we need to calculate the y coordinate?
Yeah, that's one of the details that you can look at from the the y coordinate, of course, is it's constant height, and so it's just the radius. Yeah. Okay, all right. Okay, so moving along, how do you parameterize a line? Let's see here. Well, which line? Let's suppose that we are given a point on the line and a vector parallel to the line to define the line. And very often this is the case. Very often you have a point and a direction vector, and that's how you characterize the line in the first place. And then from those, how do we produce a parameterization? So the neat observation to make is that any other point on the line, I can write a formula for this point on the line using x naught and v. And the way I do that is by observing that the difference x minus x naught is parallel to the line, as is v. That means that this difference is a multiple of v, and that means that x is x naught plus tv, namely a scalar multiple of v. So nice little handy-dandy little formula. If you have a point and a direction vector, that is your parameterization, or a parameterization for that line. Okay, so cool method? Yeah. Okay, yeah. Okay.
Could you please repeat how we included the TV?
How what now?
How we included TV there? Because I saw that x naught.
Yeah, so this is x minus x naught.
Oh.
So it's what you add to x naught to get x. That's right. Yeah. Okay. Sometimes what you want to parameterize is very similar to something that you have already parameterized. This is a really powerful method. Very often you're going to want to parameterize something that is not exactly the same, but it's very similar to something that you've already got. So in this case, keep in mind, we already know how to parameterize a circle, specifically the unit circle. There we go. There's our unit circle parameterization. Let me do this a little bit differently. There we go. There's our parameterization of the unit circle. Old news. So the question comes up, how do I parameterize the ellipse here? Specifically an ellipse with this equation. And again, high school algebra, centered at the origin, x radius 3, y radius 2. I hope you all remember all your high school algebra. How do I parameterize that ellipse? The big idea is to think first geometrically. What's the geometric relationship between what I know how to parameterize and what I want to parameterize? What's the geometric connection between them? And then just think, how do I execute that algebraically? So in particular, I know that ellipses are stretched out circles, right? So this circle has radius 1. This ellipse has what you might call x radius 3. I just need to stretch it by a factor of 3 in the x direction. And so stretching by a factor in the x, a factor of 3 in the x direction, I'm going to take literally my existing parameterization of the circle, and I'm going to multiply the x coordinates all by 3. And that stretches geometrically by that factor of 3. Right? So again, we think geometrically, what do I need to accomplish geometrically? And then I just do it algebraically. Okay. Likewise, I'm going to need to stretch by a factor of 2 in the y direction. And that's what I do by literally just multiplying the y coordinates by a factor of 2. And done. Right, so I didn't have to start from some sort of first principles. Wow, how would I have done this otherwise? I don't know. It seems like it'd be hard. I can start with something I already had and just tweak it to get my new thing. Now, if you're not convinced, right? If you're thinking maybe I've over-interpreted, maybe oversimplified this whole idea that ellipses are stretched out circles, neat observation is I don't even need to retain any of that. I can just straight up ask, is this the right parameterization? And I can plug it in, and sure enough, it works. And so that confirms that we got it right. Pretty good. That's a nice little method. So you want to sort of always be on the lookout. Again, tools in your toolbox, right? There is no single sort of like always this, no single algorithmic way to do it. But you be kind of on the lookout for, this looks an awful lot like a circle, and I already know how to parameterize a circle, and that could be your cue that this might be a foot in the door on that. Okay. All right. Very common, unfortunately, to conflate parameterizations and equations. This is a massive error. Parameterizations are really importantly different from equations. After all, parameterizations produce points. Thus, I like to describe a parameterization as being a point generator. This is quite literally the case. You plug in t and out comes points. You're making points with your parameterization. This is very much not what equations do. Equations don't make anything. What equations do is they test things. An equation is a point tester because you give me a point that either is or is not on your curve, you plug it into the equation and it will test. If the equation works, then yes, it is on your curve. If the equation fails, then no, it is not on your curve. Equations are point testers, not point generators. Right, so please be careful about that. By the way, this is why it always drives me batty. The book, our book, and most books, many books, will describe a parameterization as parametric equations, and I'm like, dude, you're conflating that with something that's really importantly different. I think that's to be avoided. Right? I really don't like the term parametric equations. We need to be making distinctions between different things, not conflating different things. So anyway. Okay, so a great example of how you can use this idea is this example right here. We're going to look for the intersection of a parametric curve and a plane. We will see later that this is the equation of a plane. You hopefully, probably, perhaps, maybe saw something like this in linear algebra. That's the equation of a plane. And the big idea is this generates points, and then we're going to test them. Generate points and then test those generated points and see which of those generated points pass the test. So here's how you generate points, just plugging into the parameterization. What comes out you test by plugging into the equation, right? The formula for x goes where x is. The formula for y goes where y is in your equation. The formula for z goes where z... Oh, gosh, colors. Formula for z goes where z is in the equation. And just see what values of t make this test actually work. And you can solve, right? This is a big equation involving t. You can solve for t. And let's see what comes out when you solve for t. You get these values of t right there. Those are the correct values of t. Now, to be fair, that was not what the question asked. The question asked, what were the points? These are the points. These are the points that were produced by the parameterization. These are the points that we tested with our equation. So if I know the t's, how do I find the points? Well, you plug into your parameterization. And so you take those values of t, you plug into the parameterization. That will produce the correct points. How we doing? Everybody happy? Yep.
So when we say we're generating points, it's almost as if we're predicting where the curve
intersects the plane. I'm sorry?
At a certain time.
We're finding the values of t where the curve will hit the plane. Yeah. Yes.
So you're just solving for t with the equation that you...
Yep. Mm-hmm. Yep. That's right. Okay, now let's see here. I can't read my own watch. Let me do like this. We have 20 seconds. All right. I don't think we're going to be able to get much done in 20 seconds. So we'll draw the line right here and see y'all on Friday. Okay. Have a good day. See you.
Thank you.
Yeah, sure thing.
Can I ask you a quick question?
Yeah, 2 seconds.